So we're going to look at what might be called in some textbooks curve fitting. And it is based on the idea that if you take an equation like y equals ax to the power of n, as you know, if we plotted that, it would be a curve. But curves are quite hard to deal with, whereas straight lines are easier to deal with. And there is a way of using the same data to plot a graph of this that comes out as a straight line graph and not as a curve, and that makes it easier to process. And we can do that by using logs. So if I log both sides of this, it could be log of any base. Usually we would use log base 10. Apply the log law to the right hand side. The log law for multiplication gets us log a plus log x to the n. And then applying the log law for powers to the right hand side, we get log a plus n log x. And the right hand side stays the same. So originally we would have had the data of x and y in a table or something, and we would have been plotting that. But now we've got this equation in terms of log x and log y, but we can still get those from that same data because you can just add two columns and plot log x and log y. And you get some extra data like this. And then the reason this is useful is because this is actually in the form y equals mx plus c. If I just rearrange that left-hand side, log x. So log y is just a variable, like y is just a variable. Log x is just a variable, like x is just a variable. N is a constant. Sorry, I knew I'd written that wrong. That's not log x, it's log a. And log a is just a constant like c. So we've actually put this into the form y equals mx plus c. And if we plotted log x against log y on a graph, so that means to literally take those numbers and plot log x on the horizontal axis and log y on the vertical axis, that would literally make a straight line graph if you plotted those coordinates. Now, why is that useful? Well, if we didn't know what n and a were, we could use this equation to find n and a, because as we can see from the way I've written it over here, n is the gradient. So the power up here is the gradient. So if I plotted this graph, took the gradient, changing y over changing x, the gradient is simply n. So if you didn't know what n was, plotting it this way allows you to find n. Equally, if you didn't know what a was, well, we can see from the way I've written it that the y-intercept is log a. And so if you find the y-intercept, log a is I'll call it c, the y-intercept, then a is 10 to the power of c. And we can find a that way as well. So this approach is useful if you suspect you have an exponential curve like this, but you're not sure what the constants in it are. So by doing this, if you get a straight line, that tells you it is an exponential curve. The gradient tells you what n is, the power, and the y-intercept tells you what a is. That is if you start with an equation that looks like this. We could also do it with an equation where we have a constant times another constant to the power of x. So this time x is the power. In the last example, x was the base, now x is the power. I can do the same approach if I log both sides. applying the log laws to the right hand side, I get log k plus x log b. So we can do the same thing, except this time log k would be the y-intercept and log b would be the gradient. So let's have a look how this could apply to a real question. So this is what a question based on this might look like. The relationship between x and y is given by y equals ax to the n, where a and n are constants. You'll hopefully recognize that as the first example that I did before. Use the data in this table to find the values of a and n and write the relationship. Okay, so just using the work that I did before, I know that I can rearrange this into log y equals n log x plus log a. So like I mentioned before, we are going to need to find log of all the y values and log of all the x values. So I'm going to add an extra row to my table for log x and another extra row for log y. And again, this just means log base 10 if I don't write any specific base. So we could work all of these out on the calculator. I've done this already. 1.00, 1.30, 1.48, 1.70, 2.00. For the y values, 1.94, 2.37, 2.61, 2.92, 3.34. Okay, and now I can plot a graph of this. Now, I can actually probably plot this quite easily on the whiteboard because all of these values are between, well, they go from 0 to 2, and these go from 0 to 4. So it's not going to be perfect, but I can have a good go at it. I'll do 0, 1, 2, and this is log x. And then vertically, log y, I've got 0, 1, 2, 3, 4, 5. Right, let me try and plot these coordinates then. So I've got coordinate 1 and 1.94, so that's about there. 1.3 and 2.37. There. 1.48 and 2.61. I've done that one. 0.48 and 2.61, so that's about there. 1.7 and 2.92. There. And 2 and 3.34. Okay, so it's ended up all clumped together because I haven't drawn it very well. But we can clearly see it's forming a straight line. That's not difficult to identify, and hopefully that's given us enough information to work out what A and B are supposed to be. So, sorry, A and N. So first of all, let me look at the gradient. Now, I can see a nice coordinate there that I could pick, and a nice coordinate up there where it crosses the corners. So if I did that, we're going up by 1, 2, 3, 4, and I've gone across by 2.5 by the looks of it. So the gradient is 4 over 2.5, which is 8 over 5, 1.6. Approximately. As it, again, you're not going to get exact values from this, and I'm certainly not when I've done it from the whiteboard. So I'm saying n is 1.6. Then to get log a, as I said before, log a is just the y-intercept. So let's have a look at the y-intercept. Well, it's looking like it's around 0.4, maybe 0.3. Let's say 0.3. So that means a is 10 to the power of 0.3, which I can't do in my head, but I can do on the calculator, and gets me to 2. So I've got that. And I found everything the question was asking. So the original equation should have been y equals 2x to the power of 1.6, having found all the missing variables.